Hey, what's going on YouTube? This video is intended to serve as a precursor to tutorial 11 because there are some very important concepts to cover before we get into the implementation. The first concept I would like to introduce is that of a shader. A shader, as is normally used in OpenGL, is designed to take a generic set of data from the programmer and allow them to access it as well as perform calculations and produce an output for specific parts of the render pipeline. There are two major parts of the graphics pipeline we can manipulate with shaders. The first part is the vertex transformations. As you remember from a couple tutorials ago, for each vertex we take the world position and perform a series of transformations in order to calculate the position on the projection plane. The vertex shaders would be able to give the graphics programmer the ability to specify exactly what calculations should be performed in order to come up with the final vertex position. Given that we've already taken care of this in our code, you may wonder why use a vertex shader in the first place. The reason for this is because we actually don't want to draw every type of object in the same way. For example, if you're drawing a GUI element, you wouldn't want to perform the same 3D transformations you'd perform on a 3D model. Instead, you'd probably take those coordinates and output them directly to the screen, or at least stretch them or transform them in various other ways. Vertex shaders give you the freedom to manipulate the vertices however you want for each different object while still providing you with a high-level interface with which to draw objects. The second part of the graphics pipeline that shaders modify is the color of the pixels. This is done in the Fragment Shader. The Vertex Shader can transmit data from itself into the Fragment Shader, as well as the programmer can set uniforms in order to modify the calculation of the pixel in the final color. The Fragment Shader is typically used to calculate things like lighting, reflections, refractions, as well as even water effects. The second concept of a shader that's extremely important is a uniform. Uniforms serve as a way for the programmer to modify data dynamically throughout the program without modifying the data in the vertex buffers. For example, it's sometimes important to change the position of the object. To do this, you would not need to change the position of every single vertex. Instead, you'd simply update a single uniform in the vertex shader that would then be used to calculate new positions of the vertex based on that updated position. It's also used for things like the camera position and changes in the camera's projection matrix. The last concept we need to worry about is luckily very simple. It's a concept known as the VertexArrayObject. When we load models, we store the positions, UVs, and normals as a normal array. A vertex array object is simply a data structure that allows you to take those data points and bind them together as if they're a single unit, as well as indexing them by a location given by the element in the set. For example, you use the element 0 to access the first 3 floats, the element 1 to access the next 3 floats, and so on and so forth. Now, one thing to note about these is they are a little bit less data efficient because you're actually doing a copy rather than just using a reference to the array. But this is not too big of a deal in most situations. In tutorial 11, the next video, we're going to implement a very basic version of OpenGL's render interface, which can be sufficient to accomplish the goals of rendering objects to the screen. So with that out of the way, let's talk about the interface that we're actually going to use here. Now, to access the vertex array object, what we're going to do is do VAO.bufferData, where you give it the location of the attribute you're binding to, the array elements, the number of elements, and the number of elements per vertex. Now, in our situation, we're going to bind at location 0 the positions, so we're going to call buffer data 0 positions, the number of positions, as well as 3 because there's 3 positions for every vertex. Now, the next thing that we need to do in the VAO is bind indices, and that's going to be used simply VAO.bufferIndices, index array, and the index count. Creating shaders will be as simple as linking a vertex shader to a fragment shader, which all inherit from a shader base class. Linking shaders will be done in a shader program class, which takes in a reference to the vertex shader and the reference to the fragment shader. In order to work with uniforms, it's going to be as simple as getting a location from the uniform allocator. Uniforms.bind and giving it a value will allocate a certain amount of space for a uniform and return back the location in which that uniform is stored. Uniforms.get or set, followed by location and the value reference, can be used to update and set uniform variables accordingly. Finally, in order to render an object onto the screen, all you need is a reference to the link shaders as well as a VAO. You pass those parameters into the render index triangle function, and just like that, you'll have the same output as the end of tutorial 10. The render pipeline is long and complex, but using our shader system that we're going to implement in the next tutorial, we can abstract it to the point of being very simple and easy to understand. At this point, you're good to head into the next video. The link is in the description. I hope to see you all there.